Hi, I'm Beqir Krasniqi, and this video documents my project for ENME489Y remote sensing. For this project, each student built a field-deployable LiDAR sensor and used it to map the geometry of an on-campus target. The final goal of this project is to create a 3D map of campus by stitching together many of these smaller maps. For my project, I chose the Nocturne sculpture. The Nocturne sculpture was built by Andrew Dunnell in 1991. After his death, Dunnell's brother and sister donated the sculpture to the school. I chose the Nocturne sculpture for two main reasons. It has interesting geometry and I wanted to see how well that would display in my 3D map. Also, it's very close to Lot 1, where I normally park, so it made it convenient. Remote sensors are devices that measure some physical characteristics of a target without making direct contact with them. There are two broad categories of remote sensor, active and passive. Active sensors contain an emitter and a receiver. The emitter emits some kind of signal, and the receiver measures some aspect of the signal that is returned to draw conclusions about the target. A passive sensor, however, does not have an emitter and relies on the environment to act as an emitter. One type of remote sensor is called LiDAR. LiDAR stands for light detection and ranging and uses light, often lasers, as the signal for analysis. The LiDAR sensor that we are using relies on a Raspberry Pi camera as the receiver. We can picture the field of view of the camera as a cone. We can then define alpha as the field of view angle, which is given on the camera spec sheet. Our sensor uses an active system with the laser acting as an emitter. H can then be used to represent the distance between the camera and the laser, and L the distance between the laser and the target. The angle between the target and the axis of the camera can be called theta. The laser spot on the target will be x pixels from the center of the camera, and the camera is known to have 640 pixels on half of its field of view. Alpha is known to be 54 degrees, which is about 0.94 radians. The ratio between the angles should be the same as the ratio between the pixels. Using this relationship, the angle theta can be determined in terms of x, pixels from the center. Finally, using right-angle trigonometry, the relationship between theta, h, and L can be established. L can be determined in terms of pixels from the center. This is a geometric LiDAR system since it uses geometry to determine distance. We can also define this conversion ratio as RPC, the radian pixel converter. This is a top-down view of my sensor. On one side we have the laser, which is the emitter. On the other side we have the camera, which is the receiver. A Raspberry Pi processes the data that I collect. An Arduino is attached to an accelerometer and sends data to the Raspberry Pi. It measures the roll and the pitch of the device. The wood supports the structure and all the components and keeps them level with one another. And on the bottom, there's a 3D printed tripod mount that's used to connect the whole device to a tripod. The tripod creates a convenient support for the device and allows easy access to move up and down. Calibration was necessary to fix small errors in device construction. For example, the axis of the camera and laser might have been off, or the distance between the two may have been more or less than anticipated. The device was calibrated by taking a series of measurements from 10 feet down to 1 foot. These measurements were then compared to the actual measurements using a tape measure. Correction factors were then added to correct the formula. This graph shows the measured and theoretical values after calibration. The red dots represent the measured values and the blue line represents the theoretical values. After changing the correction factors, they seem to match very well. The device was kept a fixed distance from the target. A tape measure was used to measure the horizontal distance of each scan. The device was then used to scan a vertical line at each horizontal location. There were many challenges to overcome while doing the project. One challenge was that the ground was uneven by the target. This was overcome by using a tripod Weather was another challenge, and it was overcome by waiting for more opportune scanning conditions. Point density became an issue and was solved by moving the camera more slowly as I collected data. The camera not detecting the laser was also an issue, which was resolved by waiting until night. Data was processed mainly by using three software programs. Python and an open source computer vision program based on Python were used to analyze the raw camera data. The Python code searched each frame for a small green circle created by the laser. After finding the circle, it recorded the pixel location of the center of the circle and took the angle data from the Arduino at each frame. MATLAB took the angle and pixel data and converted that into XYZ coordinates and created a 3D point cloud. MeshLab took the 3D point cloud and created a surface to connect the different points.